an engineering marvel renowned the world over.
It was by far the largest bridge ever built, the longest span, the tallest towers, the largest diameter cables.
Built in one of the world's most challenging environments.
You had titanic tides, you had wind and weather, and you had more than a mile to span.
Driven by a visionary bridge builder with dreams of becoming a legend.
He was a self-promoter. He sought publicity. He was a dreamer, a tinkerer.
A marriage of human ingenuity and natural beauty. It's one of the wonders of the modern world, the Golden Gate Bridge. The Golden Gate Bridge, one of history's greatest engineering achievements that pioneers numerous innovations in construction technology. To create this famous icon, bridge builders tackle immense challenges with ingenuity, determination, and a vision of greatness. The result? A melding of technology and art, and a lasting monument to the city of San Francisco.
You can go anywhere in the world today, just about, show somebody a picture of the Golden Gate Bridge and they'll go, oh yeah, San Francisco.
The rugged California coastline. For over 1,300 kilometers, it's a scenic stretch of land, a chain of wide beaches, thick forests, and jagged mountains, interrupted by a tumultuous break, where water flows between the city of San Francisco and its Marin County neighbor to the north. This 1.6 kilometer wide gap is called the Golden Gate, and it's a wild stretch of water and weather.
This is a very beautiful setting where the bridge lies. However, it's also a very challenging site.
Founded in 1776, the city of San Francisco sits right next to this rushing tempest. By the early 20th century, it's a booming metropolis of more than 400,000 people. But it faces its toughest test on an April morning in 1906. A powerful earthquake strikes, shaking the city, rupturing gas lines, starting enormous fires. The city is leveled.
The city was in a state of disrepair, damage everywhere, and it was a very challenging time in the history of San Francisco.
More than 28,000 buildings are destroyed, reduced to piles of smoldering rubble. People wander through the destruction, dazed and humbled. Almost immediately, a shared sense of civic pride takes hold, and San Franciscans vow to rebuild their city.
San Francisco was in a condition of trauma. For nearly 50 years, it had been the social and financial capital of the far West. Now it stood devastated. Could it rebuild itself? How would it rebuild itself? Could it restore itself as Queen City of the Golden West?
Within a decade, the city is back on its feet. As San Francisco continues to grow, a new invention, automobiles, fills the bustling city streets. But now, San Francisco faces a new problem. At only 122 square kilometers, surrounded on 3 sides by water, its boundaries are fixed. For continued growth, the city will need to find a way for cars to cross the San Francisco Bay. Right now, the only way over, a crowded ferry system.
Cars used to line up for hours sometimes to go on the ferry. Cars kept lining up, and they just couldn't carry the people.
It was a truly horrific situation with lots and lots of traffic problems. That was really the point where people just said, this is ridiculous, we've got to have a bridge.
Bridges. They're one of the oldest engineering achievements in human history, dating back to early wood walkways, stone paths, and brick arches. By the turn of the 20th century, bridges are crossing massive canyons and mighty rivers. To most of us, a bridge is a source of awe and wonder, spanning an impassable natural obstacle. But to an engineer, a bridge is a complex challenge, combining solid functionality and lasting strength with architectural splendor. When bridge engineers look closely at the Golden Gate Strait, they see powerful currents and unpredictable weather. In short, a tough place to build a bridge. Some say it can't be done. Others say it will cost too much. But one man sees an opportunity. His name, Joseph Strauss.
Joseph Strauss was a man of some conflicting traits. He was a self-promoter, he sought publicity, he was a dreamer, a tinkerer.
A Chicago-based engineer, Strauss makes his name and his fortune building hundreds of bascule bridges, short, functional structures that tilt up over small canals and rivers. It's a lucrative business, but lacked the glory and recognition he sought. Yet Joseph Strauss, despite his 1.6-meter height, has big dreams and a big ego to match. His goal, to build something legendary.
Joseph Strauss was the child of aspiring artists. He himself was a dreamer, a visionary. When the Golden Gate project came before him, he knew this would set him apart. This would establish his reputation for all time to come.
In 1919, Strauss meets with a San Francisco city engineer. They discuss the Golden Gate Bridge project and its challenges. It will be the longest suspension span ever built, over an incredibly deep natural channel filled with powerful currents. In addition, there's the challenge of cost, which some think will reach $250 million, and Strauss's lack of experience building long bridges. The first challenge? At over 1 kilometer in length, the Golden Gate Bridge span will stretch 213 meters beyond the current world record holder, the George Washington Bridge in New York City. No one is sure they'll succeed.
Many people felt it was impossible to build the Golden Gate Bridge. It was by far the largest bridge ever built, the longest span. By longest span, I mean the greatest distance between the two main towers of any bridge ever contemplated.
Another problem, the Golden Gate's treacherous topography. Over the millennia, as seawaters rise and fall with the ice ages, the fierce current in and out of the Golden Gate carves one of the deepest natural channels in the world, making it a tough spot for a bridge foundation.
The Golden Gate is a deeply incised channel. It's about 370 feet deep. It's scoured continually by extremely powerful tidal currents.
But the Golden Gate isn't just deep, it's fast. Here at the entrance to one of the world's great harbors, millions of liters of fresh water from the Sierra Nevada mountains meets millions of liters of seawater from the Pacific Ocean. The result, 7 trillion liters of water flowing through per day, twice in either direction with the changing tides, at speeds nearing 15 kilometers per hour. The bridge will have to withstand this rushing, raging whitewater inferno.
The average flow through the Golden Gate is about 23 million gallons per second, and that's about twice that of the Mississippi River system.
In June 1921, Joseph Strauss meets with city officials to present his design, and he makes a bold claim. He'll build the bridge for 1/10 of the costs promised by others.
When Strauss submitted his initial design, he submitted it with a construction estimate of $25 million, where every other engineer that had submitted an idea prior had a price tag associated with it of $250 million.
Officials are pleased with the cost and award Strauss the Golden Gate Bridge contract. But there's one thing they don't like, the initial design. A heavy, complicated structure based on the design of a bascule bridge.
It was widely considered to be ugly, on the verge of hideous, and even some engineers questioned whether it was technically feasible.
The ugly design proves that Strauss has one more challenge to overcome: his lack of experience building monumental bridges. His solution: if he can't design the Golden Gate Bridge himself, he'll hire a team of designers to help. He hires University of Illinois professor Charles Ellis and Leon Moisseiff, one of the country's top bridge designers.
Leon Moisseiff brought to the table new theories on suspension span design that he had developed. And Ellis was the man in the office doing the calculations. He was the mad calculator. This was the dawning of the age of American bridge building, and Strauss had the ability to bring people to the table to work with him that were top of the field at the time.
Strauss and his team began work on a new design for the Golden Gate Bridge. In this pre-computer era, the men have only a few engineering tools: pencil, paper, a slide rule, and a hand-cranked adding machine.
Faced with the unprecedented challenge of spanning the Golden Gate with a suspension bridge, Charles Ellis sat down with a paper and pencil, and stacks and stacks and stacks of calculations later, he had come up with the solution.
To build the world's longest bridge, Ellis and Moisseiff turned to a proven design: the suspension bridge.
All the longest span bridges in the world today, as they were in the 1930s, are suspension bridges. It's the only way to have a minimum structural weight in an efficient form over great distances.
The basic suspension bridge design is the same whether it's a primitive rope bridge or a modern concrete and steel structure. Anchorages in either shore hold cables that drape over towers and suspend a roadway. The structure stands with the help of two simple forces: tension and compression. The weight of the roadway and its traffic pull down on the cables, a force of vertical compression that's transferred into the towers and dissipated into the earth. At the same time, the weighed down cables are stretched between either shore, a force of horizontal tension that's transferred into the anchorages and also dissipated into the earth.
So this entire structure that's over a mile long has 4 points where the weight of that structure is transferred into the ground. The entire bridge is suspended like a giant hammock floating in the air.
To Joseph Strauss, the Golden Gate Bridge will have to balance strength and functionality with visual aesthetics. He hires Irving Morrow, a little-known San Francisco-based architect who creates detailed charcoal sketches that outline his vision. Art Deco angles, ambient lighting, and vertical panels that catch and reflect light. The result is striking.
It's so big, but it is so subtly magnificent. And the structure of it just causes your eye to feel that it is truly a piece of art.
We're not going to have a bridge.
But then a problem threatens to tear the team apart. While the design work continues, tensions rise between Strauss and his deputy, Charles Ellis. Ellis wants additional time to recalculate the tower design. Strauss becomes increasingly impatient. In 1931, their feud reaches a breaking point, and Strauss fires Ellis. With Ellis gone, Strauss is fully in control of the Golden Gate Bridge design. The chief engineer pushes forward with the planning until finally, on January 5, 1933, nearly 17 years after the process began, the city of San Francisco breaks ground on the Golden Gate Bridge. It's a triumphant moment for Joseph Strauss, but it's a tragic one for the country, mired in a deep economic depression. The depression could ruin the entire bridge project, just as it's getting off the ground. 1 in 4 Americans are unemployed, and desperate men line up by the thousands in search of food, work, and shelter. Many hope to get the chance to work on the Golden Gate Bridge.
Literally, these men would line up along the shoreline directly below where all of the construction was taking place, and they would just hang out all day long, cooking beans, waiting for someone to mess up and get fired, or waiting for somebody to slip and fall and get hurt.
Charlie Heinbockel was a friend of a bridge foreman. He was lucky to get a job, and it paid good wages.
$5.50 a day. 27.5 a week. It's good money.
Good money then, wasn't it?
In the summer of 1933, 22-year-old Heinbockel joins dozens of men to build the first piece of the bridge, the anchorages. These massive concrete foundations, embedded deep in the rock on either shore, hold the entire structure in place. Workers first excavate more than 92,000 cubic meters of dirt. Then they pour concrete for the anchorage. With help from a new technology, concrete mixing trucks. On the worksite, workers spread the heavy drying concrete by hand and foot. Workers lay the concrete and smooth it into a level plane. This part has to be perfect, or the bridge will stand crooked. And Strauss's team uses an additional innovation to combat the corrosive weather conditions at the site.
They use high silica content concrete, which was the first time ever, which has a profound impact on protecting the concrete from saltwater attack.
The next challenge for the bridge builders, the piers, concrete foundations for the soaring towers. Like the anchorages, the piers are massive, yet built to precision. Any miscalculation will render the towers off balance and make the bridge unstable. The 43,000 metric ton North Pier is relatively easy, built on a simple bedrock platform 6 meters underwater. With the Marin Pier completed in just 5 months, work on the North Tower begins. But on the south side, Strauss and his builders face an engineering problem quite unlike anything they've ever seen.
The South Tower caused probably the most delays in construction of the bridge of any aspect of it.
To reach the site, more than 300 meters out in the strong currents, workers build a steel trestle. Almost immediately, disaster. A fog-blind ship rams right into the trestle, wrecking it. Then, it's destroyed in a storm. Strauss orders it rebuilt 5 feet higher and strengthened with steel cables, but it's a discouraging beginning. Now the most difficult job begins, building the foundation 30 meters underwater on solid bedrock. It's a dangerous job for construction divers. They can only work for 20 minutes at a time during the 4 daily slack tides. And submerged in the churning water, they'll be nearly blind.
A diver dealing on this project would have had to deal with extremely low visibility conditions. The water is heavily sediment laden. Probably below about 10 meters or 30 feet, the water is completely dark.
To protect his divers, Strauss and his team create an innovative solution, a massive, watertight concrete fender to act as a buffer against the Golden Gate's strong currents. But building the 9,000 metric ton fender is itself a challenge. 30 meters down, divers in bulky diving suits use blast tubes to direct black powder bombs, blasting the bedrock flat. A giant bucket then clears the tons of rubble. It's the first time that large-scale underwater blasting has been used to build a bridge support. It's dangerous work, but it's the only way to make a flat foundation. Once the bedrock is blasted, workers lower pieces of a huge wood and steel frame into place. 22 giant concrete sections are added. By November of 1934, the protective fender, the size and shape of a football field, is complete. Large pumps suck 35.5 million liters of water out, leaving an empty hole in the middle of the powerful Golden Gate.
It looked like a huge empty pool in the middle of the Golden Gate, dewatered into dry ground.
The bedrock is now ready for inspection. An engineer and superintendent climb down a ladder inside a well 32.5 meters deep. After careful observation, they declare that the rock is solid. Strauss is ecstatic and makes a prophetic statement. The South Pier would be completed before the new year. With a major challenge overcome, work proceeds quickly. Workers pour concrete until the foundation stands nearly 46 meters tall, 13.5 meters above the water. On December 31st, 1934, as Strauss had predicted, the 272,000 metric ton South Pier is declared complete, one of the most difficult underwater construction feats ever attempted. Workers now began erecting the soaring towers, each nearly 242 meters tall. With the North Tower complete, work begins on the South Tower. Iron workers assemble about 20,000 metric tons of structural steel, piece by massive piece, in some of the most brutal winds, tides, and fog. In the early 20th century, most suspension bridge towers are made of stone or steel, making them rigid and heavy. But Golden Gate Bridge designers have to build towers that are light and flexible enough to handle high winds or powerful earthquakes, yet strong enough to hold 151 million kilograms of weight. Their innovation, a honeycomb of small, hollow steel cells, 1 meter square and riveted together. As the towers grow taller, the work becomes more precarious, especially for the rivet gangs. These teams of 4 men have to place 600,000 rivets in each tower. The rivet heater keeps a fire going at all times, heating rivets to white hot and passing them to each man who needs one through a tube.
So the task in installing a rivet is to get it into the hole red hot, to pound it in so that the essentially molten metal takes the shape of the hole, and then form the other side so that the rivet won't pop out. So the rivet has to be red hot.
There's also danger inside the towers, where men work under extremely hazardous conditions. The tiny hollow steel cells form a vertical maze. The men crawl inside to rivet sections together. 37 kilometers of ladders connect 90 designated routes through the towers. Inside the cramped 1 meter square cells, the riveting guns make a deafening noise. Even worse, the white-hot rivets melt the red lead paint right off the steel. The result, deadly lead fumes. Riveters report nausea and abdominal pain, classic signs of lead poisoning.
It was a toxic poisoning that made people weak and lose their physical stamina, and apparently their hair as well.
Strauss takes action. He requires future orders of steel to be covered with iron oxide paint instead of lead, and the existing rivet holes are stripped of their lead paint. He also has compressed air pumped into the tower shafts and provides all riveters with filter masks. It's a clear sign. On the Golden Gate Bridge, safety will be a top priority.
The people responsible for the Golden Gate Bridge were really safety conscious. Hard hats were required.
In this early era of big construction projects, planners on a $25 million bridge would expect about 25 workers to die. But Joseph Strauss isn't willing to accept that kind of loss. In addition to the innovative steel and leather hard hats, he provides safety goggles with tinted lenses. And perhaps most important, safety lines. Anyone caught stunting on the job is immediately fired. Despite Strauss's focus on safety, conditions remain dangerous. On the steel tower surface and catwalks, where men swarm like spiders, wind gusts can reach up to 96.5 kilometers per hour. Bridge workers like Charlie Heinbockel needed nerves of steel.
Some people cannot stand height, period. But I was fortunate enough I could. I did a lot of things up there which I didn't think I could ever do.
But perhaps worse than the wind is the fog. It's the essence of San Francisco. A thick, cold, wet fog that rushes through the Golden Gate Bridge almost daily. What causes this type of advection fog? Winds blow the Pacific Ocean's moist, warm air over the California coast's cold water. The air temperature drops down to its dew point, and the moisture condenses into fog. Meanwhile, hot air rising in California's Central Valley creates a vacuum, pulling that fog in through the lowest point on the coast, the Golden Gate.
Here it's not little cat feet, it's more like a herd of elephants drumbling in, and it is huge, it's heavy, it's very impactful, it's very cold.
The fog makes bridge work dangerous. When it rolls through, it blots out the sun, cutting visibility to under 1 meter and lowering temperatures by as much as 16 degrees in a matter of hours.
Fog made the footing slippery and treacherous. The winds buffeted everything. They were cold, but they adjusted.
The weather has one other effect. It's destroying the metal towers. Painters are deployed to clean all corroded steel. It's the start of a battle against the elements that continues today.
In the Golden Gate Strait, it's usually pretty overcast and foggy, so that tends to corrode the steel and penetrate the coatings.
Yet the battle against rust has an unexpected effect on the people of San Francisco. As the bridge is being built, painters use an orange-red primer as a temporary coating to protect the steel from corrosion.
The paint that's on the bridge is really based on the undercoating that sat on the steel of the bridge for many years, and people had a chance to look at it, and they just grew to love that kind of reddish-orange tone.
Architect Irving Morrow is credited for selecting the bridge's unique color. In 1934, Morrow writes a letter to Joseph Strauss. Instead of the standard silver or gray, Morrow states that an earth tone will link the bridge to its surroundings, and the orange-red primer is the perfect choice.
It's really international orange, and that is the color that Irving Morrow envisioned as blending with the Marin headlands, the hills behind the bridge to the north, as well as being a beautiful color reflecting back as you're looking at the city of San Francisco.
Summer 1935. The construction team finishes both towers, driving the last of 600,000 rivets into each. At 227 meters in height, they're the tallest bridge towers in the world. By now, it's clear something special is rising out of the water.
The Golden Gate Bridge is the most beautiful bridge in the world. And no matter where you are in the bay, it stands out very bright.
With work running smoothly, the man most responsible for the bridge, Chief Engineer Joseph Strauss, is nowhere to be found. Drained by the 10-year battle over the bridge, he confines himself to his San Francisco apartment to rest, observing the bridge through a telescope.
Towards the end of the project, Strauss disappears for a few months. Some have speculated that he experienced a form of emotional breakdown.
The towers are done. The next step, the cables. In October of 1935, workers from the John Roebling Company began hanging the massive cables that will hold the entire bridge together. The two Golden Gate Bridge cables will be the largest and strongest ever made. Each will be 2,332 meters long and almost 1 meter in diameter, composed of more than 25,000 separate wires. Each wire is about the thickness of a pencil, yet too strong for a man to bend in half. Altogether, engineers plan to string more than 28,000 kilometers of wire, long enough to circle the Earth 3 times at the equator. And each cable will weigh the same amount as one of the bridge towers, about 20,000 metric tons apiece.
The main cables, the ones on either side of the roadway, are huge. They have to be because they are bearing the weight of the suspender ropes that hang down to support the entire roadway.
Because the cables are too big to pre-assemble, all the bridge stringing will happen on the towers. Workers send wire spinning wheels back and forth across the span, laying 2 wires at a time. At first, it's slow going, but Roebling agrees to a demanding schedule. Finish the job within 12 months or lose money for every additional day. To beat this deadline, the innovative company finds a solution: spinning many wires from both ends at once.
The spinning wheels would meet in the middle and trade cables, and therefore allow about twice the speed of spinning of any method that had been used before.
Roebling's innovations deliver a dramatic increase in speed. Before long, workers are unrolling 1,600 kilometers of wire in an 8-hour shift. Roebling finishes the job by May of 1936, months ahead of schedule. To protect them, the completed cables are then squeezed together with compactors, each exerting over 73,000 kilograms of pressure. Sealed every 15 meters with metal cable bands, the cables are covered in a primer, followed by red lead paint. Now the Golden Gate Bridge is almost complete. One major challenge is still left: the suspended roadway, the counterweight that keeps the whole bridge in a perfect harmony of tension and compression. But engineers have to find a balanced way to build the roadway to keep the towers from toppling. It's a simple challenge with a simple solution: extend the roadway out from each tower symmetrically. Yet there's a surprising short-term result. While the 2 ends inch closer to a meeting in the middle, their unbalanced weights leave the roadways with a distinct angle.
You see pictures of the bridge under construction, and it looks like the ends of the trusses towards the middle are pointed up in the air and will have a big kink.
Iron workers move steel beams out in 4 directions at once, inching ever closer together toward a mid-span meeting. Vertical suspender ropes, ranging from 3 to 152 meters long, connect the roadway to the cables. Placed every 15 meters, the ropes are separated by spreaders to stop any movement. Joseph Strauss, still the bridge's chief engineer in name and in vision, rarely appears at the bridge, and even more rarely in public. Despite Strauss's absence, his presence is felt in other ways. Thanks in large part to his emphasis on safety, after more than 3 years of bridge construction in difficult conditions, the project has a few injuries and close calls, but it remains fatality-free.
Strauss felt tremendous pressure to get the bridge built in time and under budget. Strauss understood that men would work faster if they felt safer. He placed a tremendous emphasis on safety.
While iron workers continue adding beams and rivets to the roadway at a speed of more than 30 meters per day, Joseph Strauss visits the bridge and announces yet another safety innovation: a safety net under the entire roadway. Designed to catch falling workers, it's a giant step forward in construction safety, and the first-time use of this type of net in a major construction job. Over the next few months, the investment pays off.
19 individuals' lives were saved because of that investment. The press dubbed those individuals the Halfway to Hell Club.
But the perfect safety record comes to a tragic end. On October 21st, 1936, a traveling crane comes loose and collapses. It catches bridge worker Kermit Moore underneath, crushing him to death. It's a powerful reminder that bridge building is dangerous work. But then, on the morning of February 17th, 1937, tragedy strikes again. Underneath the half-finished roadway, 13 men stand on or near a 4.5 metric ton, 183-meter-long platform. Without warning, it tears away from the bridge, falling into the net. For an instant, the net holds. Then it rips free. Platform and men fall 60 meters into the water.
The safety net was designed to hold a human body, maybe 10 human bodies, but not 10 human bodies plus a multi-ton rigging platform.
Only 3 bridge workers survive the catastrophic accident. The 10 others are dead. Charlie Heinbockel was on the bridge that day, working with 2 of the victims, Chris Anderson and Charlie Lindros.
We just worked together those days as a crew. Fortunately, they separated us, and that's what happened. I wasn't there, but I could have been. Yeah, it was swept right out to sea. It was sad to see. Pretty sad.
The accident is a huge blow to Chief Engineer Joseph Strauss and the entire bridge construction crew. But the nearly completed bridge is still judged to be structurally sound, and work quietly resumes. It takes 2 more months to finish placing beams on the roadway. Then workers pour concrete, the last batches in a structure that consumed enough concrete to build a 1.5 meter long sidewalk from San Francisco to New York. As workers complete the roadway, the bridge design reveals one more innovation. The roadway deck is separated into long sections, linked with copper expansion joints. It's a brilliant move. Bridge engineers knew the steel would expand from heat, contract from cold, or shift from wind or earthquake. Thanks to these expansion joints, the bridge will flex instead of crack.
The Golden Gate Bridge, any suspension bridge, is an amazingly flexible structure, and it can move a lot. And it does on a regular basis, on a daily basis.
As the completion date nears, workers put the finishing touches on the majestic bridge. Sidewalks, railings, lights, the approach roads, and the toll booth. The Golden Gate Bridge, under construction for more than 4 years, is about to awaken to the city of San Francisco and to the world.
When the structure first emerges out of the water, that's the first milestone. When the tallest part is completed, that's another milestone. But then when the deck is finished and you can actually walk where the final users are going to walk, that's when the life of the bridge is turned on.
As for ailing Chief Engineer Joseph Strauss, he's preparing for his moment of glory. On April 28, 1937, local civic figures gather on the span to place a symbolic last rivet, made of gold. But the gesture backfires. As bystanders watch, a riveter hammers the soft metal. It breaks and falls into the water below. It's quickly replaced by a steel rivet, the last of more than 600,000 rivets in each tower on the Golden Gate Bridge. Opening day, May 27, 1937. With vehicles kept at bay for one more day, 200,000 people gather to celebrate their new bridge. Many attempt to be the first to cross in a unique way, running, walking backwards, walking on stilts, tap dancing, even riding unicycles.
And I went walking out on the bridge with my parents and my sister, and we all wore cowboy outfits. You had to have a cowboy outfit. That's my best recollection of opening day. A lot of people, a lot of noise.
For San Francisco, the day offers great cause for joy. The Golden Gate Bridge, together with the newly opened Oakland Bay Bridge, provide a way over the barriers that restricted expansion for so long.
The Golden Gate Bridge connects San Francisco to its hinterlands. Thanks to this bridge, San Francisco remains at the epicenter of what would soon be the fourth largest metropolitan region in the nation.
On the southern tower, 2 plaques are installed. One honors the men who died on the bridge. The other is a tribute to its engineers and planners, chief among them, Joseph Strauss. It's the recognition he long sought. In the end, he can claim to have directed the building of the world's longest suspension bridge over one of the world's most challenging natural obstacles, a bridge that was finished on time and under budget.
Joseph Strauss was not perfect. He had many faults. Yet he played a major role, perhaps the crucial role, bringing into being something as close to perfection as possible, the Golden Gate Bridge.
Within a year of the Golden Gate Bridge opening, 68-year-old Joseph Strauss, its champion and chief engineer, suffers a heart attack and dies.
With the Golden Gate Bridge complete in all its permanence, what was there left for Strauss to do? He was exhausted. Very shortly, he passes from the scene.
Charles Ellis, the man who designed much of the Golden Gate Bridge and hand-wrote its calculations, earns little recognition for his work. After Strauss fired him in 1931, the former professor ended up back in academia. In 1949, he died of natural causes. It remains unknown whether he ever came to San Francisco to see the finished bridge. For Chief Engineer Joseph Strauss and his team, the Golden Gate Bridge was their greatest triumph. But will the bridge be strong enough to last against the ravages of time and nature? In 1989, the bridge faces a major test when a massive earthquake hits San Francisco. The Loma Prieta earthquake, 7.1 on the Richter scale, causes nearly $7 billion in damage. Houses and freeways collapse. The Oakland Bay Bridge suffers major damage, but the Golden Gate Bridge survives intact. Engineers are relieved, but they still take action to strengthen the bridge. There could be worse to come.
There is absolutely no doubt there's going to be a big earthquake in San Francisco. We've been focused on preparing to make sure that the Golden Gate Bridge doesn't fall down when such an earthquake happens.
Today, the Golden Gate Bridge is in the final stages of a comprehensive seismic evaluation that has been underway for the last 10 years. Engineers hope the retrofit will enable the bridge to withstand an 8.3 earthquake, the maximum credible earthquake in the Bay Area. The focus of the seismic retrofit: reinforce points of strength and increase the bridge's flexibility. Ideally, the bridge will move with earthquake forces rather than resist them.
All of the steel towers on land, all the truss spans, all those towers have been replaced in the last couple of years. We've strengthened the foundations, and we've put seismic isolation bearings on top of those towers to decouple the bridge, if you wish, from the towers to minimize the forces on the structure and to allow the bridge to perform well in an earthquake.
Today, the Golden Gate Bridge stands strong. Charles Ellis and Leon Moisseff's original design, strengthened and reinforced, can handle the worst that's thrown at it. Still, the harsh natural elements are relentless, wearing the metal down and eating through the rust-proof paint. And teams of painters and ironworkers have to continue fighting back.
We have a rule that says if you put a new piece of steel out on the bridge, that you have to paint it within 2 hours, because if you don't paint it within that 2-hour time period, you're going to end up having some degradation begin just from the salt and the wind and the air.
When it comes to rust and deterioration, engineers inspect the bridge continuously. If there's a little rust, the part will be cleaned in place and covered with a protective coating. But if it's been destroyed by the elements, the part is removed and sent for repair. This is the boneyard. the bridge's very own junkyard, hidden near the base of the bridge, where workers bring corroded steel back to life. Bob Aganowski, a boneyard painter, is fixing these lacing bars.
Here's one that came off the bridge. That's what rust does to the steel. It penetrates the steel, corrodes it, and eventually falls off the metal. So what we do is we get it down to raw metal, just like it was made again, and apply a primer, which protects the steel, and then the top coating, which protects the whole piece.
If a steel bridge part is broken or must be replaced, that's where the iron shop comes in, fixing pieces and remaking the bridge little by little. Iron worker Woody Becker uses zinc, a non-corroding metal, to recast these cable spreaders, the parts that keep suspender cables from flapping in the wind.
They take down the old ones, sandblast everything, reprime it. They give it to us. We put this coating and primer inside before I cast to keep the rust out of there.
Out on the bridge, painter Lynn Wood works on the suspender ropes that hold up the roadway.
Right now our job is to paint these. So we go up in this box, we start off by prepping it, cleaning up, flaking off old paint. Then we clean it up, then we come back and we put on 3 coats of paint. This bridge is being painted constantly. There's 35 of us approximately, and we each have a different area that we take care of at different times.
As hard as these men and women work, the wind, fog, and salt water work just as hard to undo and corrode one of mankind's greatest engineering achievements.
At the bridge, it's like you just got to keep going and going and going. It never ends.
Every day is a challenge because you don't know exactly what the weather is going to be like, what you're going to face once you get here.
The natural elements challenge the bridge daily, but there are other, more serious challenges like terrorism that threaten the bridge's very existence.
Well, I think people consider the Golden Gate Bridge a target for terrorist activity simply because it is such an icon. It is a symbol not only of California, but really a symbol of the United States. And symbols are something that we have learned the hard way in the last 15 years. People are out to attack symbols.
Since 2001, bridge management has improved their security to address these threats.
Our dispatching office has a bank of cameras and monitors, and they will zoom in on that specific location. At the same time, we're sending out a patrol unit, a car, a scooter, a bicycle. We can be on scene within a matter of minutes for something that is happening out on a bridge.
Golden Gate Bridge security is also concerned with one other type of dangerous activity: suicide. Chief Engineer Joseph Strauss envisioned the bridge as suicide-proof, but to preserve the spectacular view, architect Irving Morrow designed 1.2-meter-high guardrails, low enough for most visitors to climb over. Yet officers are always on the lookout, and they prevent about 70% of all suicide attempts.
We installed call boxes on the bridge that were labeled for crisis counseling. If someone does feel despondent and they feel the need to talk to somebody, they can pick up that phone, it rings into my dispatching office. We can talk to them, or if they choose, we can patch them over to a suicide prevention counselor. And it's been really helpful.
More than 70 years ago, the Golden Gate Bridge seemed like an impossible dream. Yet visionary Chief Engineer Joseph Strauss was unstoppable. He and his team developed one innovation after another to overcome huge technical and environmental challenges. And the men who built the bridge risked their lives assembling every piece of steel, every last rivet. Their hard work and dedication paid off. Today, the Golden Gate Bridge is an icon of engineering achievement, known and admired around the world.
The Golden Gate Bridge is a triumph of engineering and a triumph of art. As engineering, it achieves the near impossible. As art, it provides us with one of the enduring icons of the 20th century, one of the most powerful symbols of our shared identity.